Hey guys, how you're doing? In this video we'll do some advanced exercise on local extrema. And this is the third video of the series that I posted here on YouTube, so check out the two previous videos if you want to do some more basic exercise. Also, I have a little surprise for you at the end of the video, so stay tuned. But now, let's start with the exercise. Grab your pen and paper and I will see you in a minute. As a first exercise for today's videos, I want to compute the local maxima and minima of the function f of x equal to e to the minus x to the power 3 plus 3x. As always, first things first, we compute the first derivative and we find the critical points. So f prime of x is equal to e to the minus x to the power 3 plus 3x, because it's e to the x, times, we have to take the derivative of the exponent, which is minus 3x to the power 2 plus 3. And we have to impose that this guy has to be equal to 0. Now, an important bit of information. This exponential here is always bigger than 0. So it can never be 0. So it cannot contribute in any way to the critical points. Therefore, the only things that we have to check is when minus 3x to the power 2 plus 3 is equal to 0, which means that 3x squared is equal to 3. I can simplify by 3 on both sides, and I get that x to the power 2 has to be equal to 1, which means that x has to be equal to plus or minus 1. Okay, so these are my critical points. Perfect. And now I can use, for example, the second derivative test to figure out if they are local maxima or local minima. So we compute the second derivative, f second of x equal. And now we have to be a bit careful because it's a product rule. So first we take the derivative of the exponential times this one taken normally, and then we're going to take the derivative of the polynomial times the exponential. So the derivative of the exponential, we already did it, so it's going to be e to the minus x to the power 3 plus 3x times the same polynomial, so I just can square it, so minus 3x to the power 2 plus 3 squared plus, and now I have to take first the derivative of the polynomial times the exponential, so I get e to the minus x to the power 3 plus 3x times the derivative of the polynomial, which is minus 6x, and the derivative of 3 is 0, so that's just minus 6x. Great. Now I can simplify a bit this expression and I can factor the two exponential. So I get e to the minus x to the power 3 plus 3x times minus 3x squared plus 3 all squared minus 6x. And now this expression is much easier to evaluate. So what we have to do, first we evaluate f second at the point 1, and this is equal to e to the minus 1 plus 2 times minus 3 times 1 is minus 3 plus 3 is 0 minus 6, which is equal to minus 6e, which is a negative number, and this implies that f second at 1 is less than 0, which means that we have, sorry for that, a local maximum for the solution. So we proceed, and we can evaluate f second at the point minus 1, and this is equal to e to the minus 1 to the power 3, so it's minus 1, so it's 1 minus 3 Now why here I wrote 2? It was a 3 here. So, okay, doesn't change that much. Is e to the power 2. Still negative. So e to the 1 minus 3 times, now I have to evaluate minus 3 times minus 1 squared is 1. So minus 3 plus 3, which is again 0. And minus 6 times minus 1 is plus 6 now. And this is equal to 6 e times e to the minus 2, which is positive, which means that minus 1 is a local minimum by the second derivative test. As a second exercise, I want to compute the local maxima and minima for the function f of x equal to e to the minus x squared over 1 plus x to the power 2. As always, the drill is the same. Critical points for first. So compute the first derivative, f prime of x, equal to what? Well, now we have a quotient, so we have to apply the quotient rule. So we square the denominator, 1 plus x squared all squared. Then we take the derivative of the numerator, which is e to the minus x to the power 2 times the derivative of the exponent, which is minus 2x, times the denominator, so 1 plus x to the power 2, minus the derivative of the denominator, which is 2x, times the numerator, which is e to the minus x squared. And we have to impose this to be equal to 0. So let's rewrite this f prime in a slightly different way. We notice that we can factor, for example, e to the minus x squared in the numerator. So we have e to the minus x squared over 1 plus x squared squared times, and now we do our calculation. So minus 2 times 1 plus x squared, it becomes minus 2x minus 2x to the power 3 minus 2x. And this has to be equal to 0. Now, among these all these three terms, we can also factor a 2x, actually a minus 2x. So we factor it, so we have minus 2x times minus 2x and minus 2x, I factor minus 2x, so I get a 2, plus x squared times e to the minus x squared, all divided by 1 plus x squared squared, equal to 0. Now, what are the terms in this expression that can be 0? So, e to the minus x squared, it can never be 0 because it's an exponential. So, I don't have to take care of this. The denominator is 1 plus x squared. And 1 plus x squared is always positive. Why? Because 1 plus x squared is always bigger than 0, since x squared is always bigger than minus 1, right? Because it's always positive. So the denominator is not a problem either. For the same reason, 2 plus x squared is always bigger than 0, since again x squared is bigger than minus 2, so it's always positive. So the only terms that actually can be 0 is minus 2x, and minus 2x is equal to 0 only if x is equal to 0, which means that x equal to 0 is my critical point. Is my unique critical point. Now, I can use again the second derivative test, but the derivative is a bit cumbersome. And instead, the first derivative test is a bit easier. Indeed, we can do the sign chart of f prime. and we know that the only 0 is for x equal to 0, and the denominator can never be 0, so we don't have any vertical asymptote, so we are really happy about it. And then we can evaluate the expression for x equal to 1 and for x equal to minus 1. And now we have to be a bit patient and do it. So we have to evaluate this guy for x equal to minus 1 and for x equal to 1. Now, for x equal to 1, we have minus 2 times 2 plus 1, which is 3, e to the minus 1 divided by 1 plus 1 squared, which is 4. Now, this number, I don't know what it is, but it's definitely negative. So at minus 1, the function is negative. At 1, the function is negative. Minus 1, I still have to compute it. And for x equal to minus 1 now, sorry for this little play. So x equal to minus 1. I can evaluate the same expression, and I get minus 2 minus 1, which is 2, times 2 plus minus 1 squared is still 1. So this is 3 times e to the minus 1 divided by 1 plus minus 1 squared is still 1, all squared is still 4, and this is positive. So I have a positive sign for x equal to minus 1, which means that my function now will do this. So let's rewrite the sign chart down here. So we have 0. We know that at minus 1 is positive, so here is positive and here is negative. And what does it mean? It means that my function will increase up until 0, and then it will decrease afterwards. Therefore, at 0, I have a local maximum. And now, an exercise on local extrema for trigonometric function. I want to find the local max and min of the function f of x equal to 2 times the cosine of x plus the sine of x squared in the interval 0 to 2 pi. Okay? And I'm going to assume that it's 0, the one that is inside the interval, and 2 pi is not in the interval. Okay? Otherwise, the function will repeat itself, and I will find infinite local max and min, probably. The drill is always the same. We take the first derivative, f prime of x. And now the derivative of the cosine is minus the sine, so this is minus 2 times the sine of x, plus the derivative of the sine square is 2 times the sine of x, times the derivative of the sine, which is the cosine of x. And I want to impose this to be equal to 0. We can factor 2 sine of x between these two terms, and we get a minus 2 times the sine of x times minus 1, plus 1 minus the cosine of x is equal to 0. And when does it happen? This happens only when the sine of x is equal to 0, and the sine of x is equal to 0 only when x is equal to 0 or x is equal to pi, and the cosine of x minus the cosine of x plus 1 is equal to 0, which means that the cosine of x has to be equal to 1, and the cosine of x is equal to 1 only when x is equal to 0. And now how do we proceed? Well, we can use or the second derivative test here, or we can still use the first derivative test in a slightly different way. And I want to show you how to do it in this case. So the things that I do is that I draw my unit circle, and then I draw the angles corresponding to x, to the critical points. So which is x equal to 0, which is this angle, and x equal to pi. this other angle. Now I have that my unit circle is divided into two parts, up above and down below. And now I can proceed as I will do with the first derivative test. So drawing the sign chart, but now the sign chart has to be drawn on the unit circle. And in particular now, since I have only these two arcs, I have to evaluate the function in a point in this arc up above and in one point in this arc down below to figure out which is the correct sign. And in particular, I will pick x equal to pi over 2 and x equal to 3 over 2 pi. And why I do this? Well, because for this angle, the value of the sine and the cosine are particularly easy. Indeed, x equal to pi over 2 correspond to this 90 degrees angle. And here, the sine of this angle is equal to 1 and the cosine is equal to 0. And for x equal to 3 over 2 pi, correspond to this angle here. And I know that in this case, the sine is equal to -1 and the cosine is still equal to 0. So let's evaluate the first derivative at these 2 points. So the first derivative is this guy here. We can copy, put it here. And now I want to evaluate this for x equal to pi over 2. And for x equal to pi over 2, I have -2 times 1 times 1 minus the cosine of pi over 2 is 0, so 1 minus 0. This is -2, which is negative. And for x equal to 3 over 2 pi, I get -2 times -1 times 1 minus the cosine of 3 over 2 pi is still equal to 0. So this is 2, which is bigger than 0. Now, what does it mean? Let's go back to the unit circle. It means that up here is positive, the function, and down here, sorry, the opposite. That up above here, the first derivative is negative, and down below is positive. So at the point x equal to pi, the first derivative is negative first, and then it goes up, which means that we have a local minimum. And at the point 0, the first derivative first goes up, and then goes down, which means that we have a local maximum. So from this plot, we deduce that x equal to pi is a local minimum, and x equal to 0 is a local maximum. And now the little surprise. I prepare a code in Mathematica that automatically does the first and the second derivative test, so you can do your exercise and then check them out using this Mathematica code. But how it works is very simple. You just give me the function f of x, in this case is x to the power 3 minus 3x squared plus 2. You press shift enter, and the code will tell you that you have two critical points, one at x equal to 0 and another one x equal to 2. Then x equal to 0 is a local maximum and x equal to 2 is a local minimum. You can use this code to check out your exercise and to train for your final exams. You don't have really to take care of anything that's written there, just it automatically does the first and second derivative test for you. And you can always change the function f of x to something else. For example, we can plug the first function that we encountered today, plus 3x. You press play, and you find that this function has a local maximum and x equal to 3 over 2. And this is the plot of this function. So I hope you like this little also detour in computer science somehow, in programming. And if you want to see more content like this, just let me know in the comment. That's all I have for you for today. See you next time.